Welcome to second seminar in EMC web seminar series. Today we'll look at what is ESD or Electrostatic Discharge. First, ESD, if you look at the term, electrostatic indicates it's a static electricity, and D is a discharge, so it means it's a discharge of a static electricity. ESD is probably the most familiar EMC term. Almost everybody knows about ESD, but however, I think familiarity is often limited to the term, with most people not knowing much beyond that. This seminar will give some insight into this subject. The word electrostatic indicates it's a static electricity. In science class, you may have done some experiments with static electricity. For example, if you rub a glass rod with static electricity, or if you with silk cloth, or if you rub a piece of amber with wool, the glass and amber will develop a static charge that attract small bits of paper or plastic. If you connect this glass rod to a metal object, then all the accumulated charge will be discharged, and that's called an ESD event. The electrical spark or shock you sometimes experience when you touch a metal shelf in store is another example of ESD. And you may ask, why am I not just seeing a spark or electrical shock every time I touch a metal shelf? The reason is the amount of electrostatic voltage being generated or peak amplitude depends on relative humidity as well as the peak voltage, material involved. So higher the humidity, actually the charge will not be able to accumulate enough. There is a leakage path available, and you will see a lesser amplitude. So you can see, like, if humidity is high, the line or peak amplitude is lower. It also depends on the material involved. So suppose if you take a wool as an example. If you have, in case of a wool, maximum amplitude or static electricity is like a 5 kilovolt if humidity is very, very low. But if somebody say wearing a synthetic clothes, in that case, and if humidity is low, like is like a typical office room without humidity control, or like an Arizona desert kind of weather, in that case you may see up to like a 15 kilovolt of static electricity. And when you discharge this electricity quickly, like by touching it to a metal object, you may see a huge current spike, and that can have some damaging effect. Now, let us look at some common examples of how much static electricity you can generate if you do some activity. Like first is, if you're walking across a vinous road, if humidity is like just low, like 20% relative humidity, it can generate 12 kilovolt. Right? The same activity at 80% humidity will be like just a quarter of kilovolt. If you are walking across a synthetic carpet, at a 20% humidity, you can generate 35 kilovolt. But again, at 80%, it's just like 1.5 kilovolt. If you are doing some of the activity of printed circuit board, like aerosol circuit freeze spray, at 20% humidity can generate 15 kilovolt of static electricity. But at 80%, it goes down to 5 volt. Now the next one is on the same why ESD. Like if you look just for practical purposes, ESD is mostly associated with human interaction. If any is subject to human interaction, then ESD event could occur. It is possible that a machine can also generate an ESD event. However, its scope is limited compared to that of human interaction. ESD is a context-sensitive subject. The effect, testing, and solution depends on the environment. If you look at embedded system, then we are mainly looking at three perspectives. One is a semiconductor, or like IC integrated circuits that's being used in that embedded system. A system manufacturing, so when you are putting all the components on printed circuit boards and creating a system. And third is an end user, so when an end user uses that system, what happens? There are mainly three perspectives for embedded systems. We look at each of them for an ESD. So first, let us talk about the semiconductor perspective. Microchip technology is a semiconductor manufacturer. We'll also look at the microchip perspective. Semiconductor device goes through lots of human interaction before it is mounted onto a board. It is possible that device may be subjected to an ESD event during this period. Almost all CMOS devices tend to have a protection circuitry to avoid damage in this condition. And it's called like an ESD protection circuitry. And as a part of a quality process, microchip devices are tested against two Jeddah standards. They are, first one is called JESD22-A11-4B for human body model, and second one is same JESD22-A11-5A for machine model. If you are looking for more information and test levels and other stuff, please refer to Microchip Overview, Quality System and Customer Interface Handbook. If you go to a Microchip website from Microchip homepage, you will find a link for quality and environment homepage, and from that page, if you go to a quality and reliability homepage, you will see this handbook. The document number is TS00169 and it's available in a PDF format. Now if you look at these two models, human body model and machine model, the human body model it generates a waveform that is similar generated by human interaction. And machine model waveform is a little bit different. Machine model generates a cyclic waveform. It may look something like this, but and in case of machine model, there is no resistance. So depending on the resonance of the system, you may see an infinite waveform. And if you look at the test limits, most of the time machine model test limits are 1/10 compared to human body model. Now when we talk about the semiconductor or component level testing, it's different than a chip level testing. The most important thing here is that during this testing, devices are not biased, they are not powered. So this test verifies the ESD behavior of a device when a human handles it. For example, when you touch a device without wearing an anti-static wristband. The next perspective is the manufacturing perspective. So as a customer, when you buy this semiconductor device and you pop it on the PCB boards and you create your system. So at that time, again, human interaction as well as the machines, they can generate an ESD event. And to avoid those ESD conditions and damage the system during manufacturing, what we are talking about something like anti-static workstations, wristband, grounded systems. Now, when we talk about the manufacturing perspective, it's mostly driven by quality system of that company, and that varies a lot depending on the industry. Now, the next perspective is an end user perspective. That's the third and last one that we'll discuss today. Most systems require human interaction which can generate an ESD event to the interior of the system. So most of the people, when they send or they sell their complete system to their end user, it's packaged in maybe some kind of exterior or enclosure. And when human touches the exterior surface of that enclosure, they can create an ESD event on the exterior side, and this perspective handles that condition. Now if you look at whatever we discussed about semiconductor perspective, in case of semiconductor, we were directly injecting ESD event on a device. In this case, the testing is performed at an exterior surface of the system, or like an enclosure of the system. So this testing is quite different than the first testing. In this particular case, depending on the package, depending on the location of the electronic circuits and cables, and also the leakage path in the system will see a totally different behavior. And to address those testing requirements, there is a different standard from IEC, International Electrotechnical Committee. It's 61000-4-2. This standard defines, it's a system level standard. It's not a semiconductor, or it's not intended for an end user manufacturing environment. It defines test voltage waveform, various test levels, the type of test equipment you should use, test setup, as well as the test procedure. If you look at test equipment, what we have is, first you have a high voltage DC supply. So depending on your peak testing voltage, like if you need to test at 10 kilovolt, this source should be able to generate 10 kilovolt of DC supply. Now, in first phase, this switch is closed, and this DC voltage charges this capacitor through this register. Now, once this capacitor has been charged, this switch, the source switch, will be opened, and now the capacitor is holding a charge. Now this capacitor is quickly discharged using this 330 ohm resistor. So this switch is closed to create a discharge event, and the current will flow to this path. And considering that this register value is very low, it creates a huge current, and we'll see some numbers in upcoming slide. Now, if you look at a test waveform, it looks something like this. Now, if you look at x-axis is your time, and y-axis can be either a peak voltage or peak current. Now, if you notice that it has a huge spike, and if you look at the rise time, it's just 0.7 to 1 nanosecond. And there are two interesting data points in this waveform. First occurs at 30 nanoseconds, and second occurs at 60 nanoseconds. And we'll see some important parameter at these data points. Now, if you look at the test levels, it depends on the discharge method. There are two types of discharge method. First is called contact discharge. In case of contact discharge, the electrostatic discharge occurs directly on the system. Like they use a sharp needle, and it's being directly touched to the metal object or metal portion of the enclosure, and direct discharge is generated. In case of air discharge, round needle or round point is used with an ESD gun, and discharge occurs through air. And that's why if you look at most of the test point, in case of air discharge, voltage tends to be much higher than contact discharge. There are levels of testing, and depending on the environment, you need to select the right level. Suppose if you look at a fourth level, and for level 4 requirement, the test voltage for contact discharge is 8 kilovolt, and for air discharge, it's 15 kilovolt. Earlier we looked at an ESD waveform and we saw some important test points. So now let us look at those test points for various test levels. Now if we again just focus on level 4, you will see that at level 4 we have an 8 kilovolt peak amplitude. This results in a peak current of 30 amperes. And this is simple enough. You can have an 8 divided by 330 ohm and you can get this number. Rise time is extremely fast, just 0.7 to 1 nanosecond. Now if you look at the current at 30 nanosecond, we are still looking at 16 amperes, and at 16 nanosecond it's like 8 amperes. Most of the embedded system cannot handle this much current, and that's why in some cases ESD can have a destructive behavior. Now when we have different test levels, how we select what level we should use for testing. The IEC standard recommends some method for test level selection. It mainly intended to replicate the operating environment of the system. So first what you need to know is you need to know the minimum humidity or relative humidity where the equipment will operate. Then type of material you use, and that will determine the peak voltage you may have. So if your equipment is, say, suppose it uses an anti-static material, then depending on humidity, say suppose if humidity is higher, like 35%, then you can just go for class 1. That means a 2 kilovolt peak level requirement. But if you use a synthetic material and minimum humidity, possible minimum humidity is like just 10%, then you need to go for level 4. And if your conditions are even worse than that, then you can use that special open section and you can test even higher. It mainly depends on the environment. Now, how you perform a testing? If you look at IEC standard, it recommends various testing methodology depending on the equipment you use or type of equipment you are using. We just look at one as an example. In this case, first basic primary equipment is your ESD gun or your test equipment that generates an ESD event. What you have is an earth plane or a conductive surface. Over that you need to have an insulating material where you will put your equipment, and the ESD gun is grounded, connected to earth, and you need to create an ESD event. Like it can be a contact discharge or it can be an air discharge. Depending on discharge method, you need to change the tip of the ESD gun, and you need to create the ESD event on a various exterior surface of your equipment. And also IEC also recommends what you need to try. You need to test it, and we'll see it in the next slide. There's also another way of testing is to do an indirect ESD event. In this case, you need to use a vertical coupling plane. So here we have one vertical coupling plane or metal object that's again connected to ground through resistor, and we are creating an ESD event on that vertical coupling plane, and that indirectly transfers a charge to an equipment that we are trying to test. So this is one of the test setup that you can use for floor standing equipment. Please refer to an IEC spec for other configuration. Now when you are testing it, what test point you should use? Now when we talk about ESD, what we are trying to do is we are trying to create an electrical spark. A spark generation is not an exact science. It is very unpredictable. It is difficult to precisely reproduce the results, therefore it requires experience. It is possible that different test engineers may come up with different measurements, and therefore the IC standard suggests ways to verify the test setup as well as the test point to better reproduce real-world events. You need, before you start testing, you need to make sure you are generating a right waveform. Then, during your testing, you need to select the right points for testing. Now, the main intent here is that the equipment can have a human interface. So if you have any areas in the equipment that may have chances of a higher human interaction compared to other sections, then you need to test them. A few examples are like electrically isolated metallic sections, control or keyboard. That will be the number one area where there will be human interaction. So you need to have a EST event on those areas. Then indicators, LEDs, slots, grills, connectors, hood, any such things. That will be the next point for testing. If you suppose you have an EST issue or your equipment is subject to human interaction and that can have an EST event. So how you address those EST issues? There are multiple ways to address EST concern. The number one is a material selection. And the reason why you need to address EST concern is you've seen that EST signal has extremely fast rise time and a huge peak current. It can be as high as 60 amperes, and that's why it makes it a real tough noise to handle. Now, if you look at a material selection, then a multiple type of materials available. You may have an insulating material, antistatic material, static dissipative, or a surface resistive material. Each material has a different characteristics and different EST behavior. Like in insulating material, depending on what you use, like a polyethylene, PVC, ceramic, rubber, they may be used in application in protecting components against EST by creating enough insulation. But at the same time, some of them can generate more EST. Antistatic material is one of the popular choice to reduce an EST. What it does is it does not allow enough electrical energy to build up, and that way it limits the peak energy. But considering there are so many materials are available and depending on environment, it's better to choose the material, select the material and understand their properties. The next thing you can do is, you know that there will be, when there is a human interaction, there may be an EST event. So determine the first point of contact and see how that EST event can be transferred to a susceptible or some component that is sensitive component to ST. In case of most of the EST fixes, the primary goal is to identify a sensitive component in the system and keep energy away from that sensitive component. Once you determine the first point of contact for an EST event, that will help you in identifying or help you in focusing your efforts. If you can take some effort on that point itself to divert energy, then it will not go to the sensitive part of your system. Second, most of the EST, the main reason EST is destructive is its current. It can be very high. So if you limit the current, then it can significantly reduce the destructive behavior of EST. So in a simple way, you are just talking about adding some resistors in various parts to limit current. Also, you need to use a low inductance ground. Suppose if your ground inductance is very high, and with this much high EST current, it can result in a ground bounce, and it can upset a whole system. That's another typical fix. And in future seminars, when we discuss tips and tricks, we look at specific examples. But here, right now, these are some of the typical way to fix EST. And that ends the build or discussion on what is EST. For this presentation, we looked at an IC spec, and if you are interested, you can buy the IC spec from IC website. Please Please give your feedback on the EMC seminars, what you feel, what you would like to see, and that will help us in improving the EMC seminars. Thank you.